Hello everyone. I hope that all of you are fine. Welcome to another lecture of robotics and automation. And in today's lecture, we shall continue about the industrial communication. If you remember the previous lecture, we talked about different communication methods. We have discussed about network topologies, and then we have talked about medium access methods. And finally, we studied about the OSI model for communication. So today we shall go into a little bit deeper, and we shall study the communication protocols. Then we shall talk about types of communication and different types of field buses, Modbus, Profibus, and finally CAN bus. So let's begin. Some of the most widely used control protocols in use were developed by important suppliers of automation equipment. 3 suppliers are mentioned below. The first is Modicon. Modicon built the first PLC ever used. It was one of 3 functionally similar controllers installed as a transmission plant of a General Motors subsidiary in 1969. Modicon was an independent company for about 8 years before it was purchased by Gould in 1977. Then by AEG in 1994, Modicon has been owned by Schneider Electric since 1996. Modicon remains active in the PLC EAC market around the world. It has maintained a significant market presence over 40 years. The second is the Allen Bradley. Allen Bradley, a prominent manufacturer of electrical equipment, was the dominant PLC supplier in the United States by the mid-1980s. It was by far the main PLC supplier to car and truck manufacturers. Like Modicon, it has a large international presence. In the late 1990s, Rockwell Automation bought Allen Bradley. It still has a sizable market position. The last is the German multinational company Siemens. Siemens had a large market position in Europe by 1990. It now has a worldwide presence. Siemens collaborated with other German companies and Bureau of the German government to develop the Profibus protocols. Okay, so the next thing is interface standards. So before we go to the actual protocols, we need to understand what are the interface standards that are being used in the communication, especially in the industrial communication. So the first one is the RS-232. The RS-232 is a Telecommunication Industry Association standard for data transmission at speeds up to 20,000 bits per second. It is used for serial data transmission. RS-232 is used only for data transmission from one device to another. RS-232 interfaces were built into many legacy computers and devices like controllers and printers. RS-232 ports most often have D-shell 9-pin, 15-pin or 25-pin receptacles. Most RS-232 cables have male ends. In cases where the numbers of pins differ between connected devices, an appropriate cable will be needed. These can be obtained from electronic suppliers. RS-232 cables can be no longer than 50 feet. RS RS-232 ports have been replaced by USB ports in contemporary use. So in the new computers you find you shall find USB ports now in the newer computers, and these old serial ports they have been gone. USB allows far faster data transmission with a simpler cable. However, many controllers are so reliable that they are used for 15 years or longer. So the typical reader may have seen RS-232 ports and cables. Okay, so the next standard is the RS-485. RS-485 is an interface standard for data communications that allow much higher data transmission speed than RS-232, up to 1 megabits per second on a 100-meter cable. Data communication speeds varies inversely with the total length of the RS-485 cable. The shorter the total length, the faster the maximum speed, and vice versa. At RS-485 terminals and on conductors, a small negative voltage represents an off bit and a small positive voltage represents an on bit. Okay, so these were two standards, interface standards we have, and now let us see what is a protocol. The simple definition of protocol is a method for digital data communication between two or more devices in different locations or on a network. So when digital devices communicate two or more, so then there we need a method for communication, and this is called protocol. Okay. For example, TCP/IP is a protocol, communication protocol, and TCP transmission control protocol and IP is the internet protocol known as TCP/IP are key protocols. They are used together on the internet and in Ethernet networks in commercial and government organizations. TCP/IP is a standard for transmitting data in packets from one computer to another. The two parts are TCP, which deals with construction of data packets, and IP, which routes them from machine to machine. So TCP deals with the generation of data and construction of data, while IP is for routing, finding the shortest route so your data can reach the destination. IPv4 uses 4 octets for a sum of 32 address bits. The decimal equivalents of each octet range from 0 to 255, and periods separate octets in an IP address, e.g. 192.168.41.23. Like typically you see in your local area network, you see these kind of addresses on computers and sometimes routers or other devices that are connected. So yeah, there are restrictions regarding IP addresses. Some can't be used, and the Internet Protocol version 4 is quickly running out of available addresses for public access. TCP/IP is mentioned here because some protocols used in control applications are adaptations of TCP/IP. For example, in Modbus TCP/IP, TCP/IP is like an envelope for data transmitted per the Modbus protocol. In these applications of TCP/IP, data is sent from one node to another on a network using the same node addressing scheme that IP uses. In the late 2010, IP version 4 is being used around the world. IP version 6 with 128 address bits will eventually replace IPv4. Okay, so the next one The next topic is types of communication. So deterministic communications, communications that occur within predictable and repeatable time intervals, are referred to as deterministic. In controllers, deterministic communication capability is vitally important. Most programmable controllers check and see if any inputs from the field devices have changed many times per second. If any have, the controller responds rapidly. Deterministic communications is also referred to as cyclic communications, notably in the Profibus standards. So this Profibus we shall study in the upcoming slides. Ethernet is non-deterministic communications occur on an as-needed basis. But some industrial communications protocols use deterministic adaptations of Ethernet, like we talked about Ethernet IP. Use of managed switches effectively makes most networks deterministic. However, switches used in industrial Ethernet networks should be segregated from office networks to ensure determinism. So we have communications, we have PC to PLC communication, we have PLC to PLC communication, and communication between different modules. So here you can see a communication network of industrial communication system. We have this is supervisory control and data acquisition. We have a main computer, and then we have a server, and these are connected by the Ethernet, okay, and they are connected to the gateway, and also they are connected to each other. And then if we go to the one step lower, we have PLCs, we have here embedded controllers and converters, and they are all connected to some sensors and some other devices by RS-485 types of communication bus, which is a serial communication, or they can also be used here Modbus RTU. So you see that different levels have different communication demands. Here on the lower level you have more like something like a real-time communication should happen, because there is less data and more of less, also the delay time should be less. But here on the top level you have more data, but there can be some amount of delay is also acceptable, because here you don't need control, here is only supervision. But here you are doing control using PLC, that's why here you need fast communication. MPI, which is multi-point interface bus, is designed for programming and data services on devices. It is not designed to collect data from decentralized peripherals. In a network, there must be at least one master which manages data flow on the network. Network speeds is optional, 9 kilobit per second to 12 megabit per second. In principle, transmission distance is not limited, but the network is primarily intended for local road length in tens to hundreds meters. Transmission technology is addressed through the RS-485 communication standard transmission and by fiber optic supplemented with converters, but this solution is not commonly used. So the disadvantage is that it has limited amount of data transferred, longer response time, and short range network. So here, as you can see, that there's a communication between a PC and a PLC, and here we have some kind of communication module, and here this is connected to USB cable, and here you have, and the module is connected to the inputs and outputs of the PLC. So that's how the communication happens. But this type of communication is not really applicable if you need a really high data transfer. The speeds are higher. For example, you cannot use this thing with in real-time control situations where just slow, fast response time is required. Okay, so this was PC to PC communication, PC to PLC communication. Okay, and now what about PLC to PLC communication? PLC to PLC communication, communicated by several items. We can use Profibus, we can use Profinet, we can use CAN bus or Modbus, and several other maybe. So let's begin with the basics of what is these buses came from. So let us talk about first field bus. What is field bus? Field bus is a name of a family of industrial computer networks used for real-time distributed control. A complex automated industrial system is typically structured in hierarchical levels as a distributed control system. In this hierarchy, the upper levels for production management are linked to the direct control level of programmable logic controllers via a non-time critical communication systems, e.g. Ethernet. The field bus links the PLCs of the direct control level to the components in the plant of the field level such as sensor, actuators, electric motors, console lights, switches, valves, and contactors, and replaces the direct connection via current loops or digital input-output signals. So here you can see what the field bus does is that it links the PLC of the direct control level to the components in the plant of the field level. So you have a control level, and then you have a field level in a distributed control system. Okay, so I should make another color. So you have direct control level, and then you have field level here. And if you see the upper levels of production management, the upper level is for management, production management, and upper level for production management. So here, as we have seen already, so this is the field level here. This is we call field level. And we have control level, and finally we have management. So we have these three levels. So what does this field bus does? It connects these control level to the field level. Okay, the requirement for a field bus are therefore time critical and cost sensitive. Since the new millennium, a number of field buses based on real-time Ethernet have been established. These have the potential to replace traditional field buses in the long term. In this way, it is a way to connect instruments in a manufacturing plant. Field bus works on a network structure which typically allows star, ring, and tree network topologies. Previously, computers were connected using RS-232 or serial connections, by which only two devices could communicate. This would be equivalent of the currently used 4 to 20 milliampere communication schemes, which requires that each device have its own communication point at the controller level. While the field bus is the equivalent of the current local area network type connections, which requires only one communication point at the controller level and allow multiple hundreds of analog and digital points to be connected at the same time. This reduces both the length of the cable required and the number of cables required. Furthermore, since devices that communicate through field bus require a microprocessor, multiple points are typically provided by the same device. Some field bus devices now support control schemes such as PID on the device side instead of forcing the controller to do the processing. Okay, so types of field bus we have Modbus. This is a type of again a field bus. So Modbus and its variants. The original proprietary Modbus protocol was developed by Modicon in 1979 for use with Modicon PLCs. It is one of the earliest control protocols ever developed. Data transmissions in Modbus is serial, one bit follows another. In 2004, Modbus became an open protocol managed by Modbus Foundation. Modbus is a relatively simple protocol that uses numbering schemes that are familiar to those who have programmed Modicon PLCs. Some commercially available instruments, meters, indicators, and actuators are Modbus compatible. It is correct to refer to Modbus as a control protocol, but it can also be used for data communication applications that don't require control capability. Many commercially available transmitters and indicators are Modbus compatible. The Modbus protocol uses corrector, serial communication lines, Ethernet, or the Internet Protocol suite as a transport layer. Modbus supports communication to and from multiple devices connected to the same cable or Ethernet network. For example, there can be a device that measures temperature and another device to measure humidity connected to the same cable, both communicating measurements to the same computer. Modbus is often used to connect plant system supervisory computer with a remote terminal unit or RTU in a supervisory control and data acquisition system in the electric power industry. So you see that here, plant system supervisory computer with the remote terminal unit. So you can use here the Modbus. So this was actually the one type of field bus we have, and this can be used for PLC to PLC communication also. And the second type of field bus we have here is the Profibus or process field bus. Process field bus standards arose from the efforts of consortium of German companies including Siemens and the German government. These standards and the foundation field bus standards have many similarities. The Profibus standards are maintained by Profibus and Profinet International. PI test vendors' equipment for conformance to the applicable standards. These protocols are all open. The Profibus protocols are not as widely used in the United States as they are in Europe and Asia. It supports deterministic communication. So the first thing is it is deterministic, or it supports at least. So this means that it can be used for real-time control applications. 126 network nodes supported can optionally be configured with redundant cabling. Okay, so Profibus is an industrial field bus used for all areas of automation. At the level of physical layer, Profibus is specified to suit the diverse needs and to support majority of industrial applications such as linking remote controller peripherals to procedural controller or procedural automation. Profibus DP, which is decentralized periphery, is the simplest and highly predominant variant of Profibus. It is suitable for fast transfer of decentralized peripherals and remote input-output units. Communication medium is either so I think here we have an error. It's twisted. So either a twisted pair, standard RS485, or optical fiber at speed of up to 12 megabits per second. Comparing to Ethernet, Profibus is less powerful and flexible network. System architecture network, semantic net. Okay, so here we have the diagram which shows the Profibus, how it connects. So what happens is that Profibus uses a hybrid access method. So communication between active stations is based on token ring. If you remember in the previous lecture, we talked about this methods of communication or media access methods. So we have one was random, and then we have token ring, and then master slave. So this Profibus, it uses two of them. One is the token ring, and the active stations, they use token ring for communication access, and the passive stations, the slaves, use master slave concept. Okay, so here you can see that we have a computer, and then you have PLCs, and PLC1, PLC2, and then computer, and they can communicate with the field level devices, which are some sensors or some actuators, and they can communicate with using the Profibus. And if there is a communication between these devices, it is like a token ring. Okay, and if you want to communicate with the passive or slave devices, then it's like a master slave communication. So this is how Profibus works. And then we have one more type of protocol, which is the CAN bus protocol. This is also a type of field bus, and let's look some of the history. During 1980s, to solve communication problem between different control system in cars, the German company Robert Bosch GmbH first developed the controller area network for the automotive industry in order to connect the transmission, airbags, anti-lock braking, cruise control, electric power steering, audio system, power windows, doors, mirror adjustments, battery and recharging system for hybrid electric cars. So it was developed by a German company. So it can be it's clear from the name that it's controller area network. It has something to do with control systems. The concept of CAN was that every device can be connected by a single set of wires, and every device that is connected can freely exchange data with any other device. CAN soon migrated into factory automation marketplace. So in contrast to the serial communication, which is RS-52, there is only peer-to-peer communication, but in the CAN, every device can communicate with other device. CAN is a two-wire differential serial communication protocol used for real-time control. So means it must have some deterministic communication. The CAN bus protocol was originally developed CAN is a multi-master peer-to-peer network message broadcast system that specifies a maximum signaling rate up from 125 kilobits per second to 1 megabits per second. It provides for 2048 different message identifiers. Okay, so yeah, one more thing is that CAN is multi-master, so you and peer-to-peer network. Okay, now let's quickly see its benefits. So the first is that it is low cost. ECUs, which stand for electronic control units, communicate via a single CAN interface. For example, not direct analog signal lines, reducing errors, weight, costs. The second benefit is that it is centralized. The CAN bus system allows for central error diagnosis and configuration across all ECUs. So I think here CAN bus is enough to write. So it is centralized, and this system allows for central error diagnosis. Okay, this is again an advantage when everything is centralized. So the error diagnosis also becomes centralized. Then you have robustness as an advantage. The system is robust toward the failure of subsystems and electromagnetic interference. So if you see here the CAN, you have different CAN nodes here. You can see they are communicating with each other, and so it is quite robust for the against the noises, and if any device fails here, so it's not really a problem. It's efficient. CAN messages are prioritized via IDs so that the highest priority IDs are non-interrupted, and this is also very interesting and very important aspect of CAN bus. So you give here priority to some of the devices, and so that's how the important devices will be given priority for communication. So this makes the communication overall very efficient. Flexibility. Each ECU contains a chip for receiving all transmitted messages. Decide relevance and act accordingly. This allows easy modification and inclusion of additional nodes. Since it is like every device can receive messages and all the devices working on the same page. So that's why changing a device is quite easy, and this makes CAN bus quite flexible. Now, where we can use a CAN device, it can be used in transportation systems like rail, vehicle, aircraft, marine. It can be used in the industrial machine control systems. It can be used in home and building automations. It can be used in mobile machines like construction and agriculture equipment. And finally, it can be used in medical devices and laboratory automation, as well as in many other embedded and deeply embedded applications. CAN data transmission uses a lossless bitwise arbitration method of connection resolution. This arbitration method requires all nodes on the CAN network to be synchronized to sample every bit on the CAN network at the same time. Therefore, some call CAN synchronous. Unfortunately, the term synchronous is imprecise since the data is transmitted without a clock signal in an asynchronous format. All nodes are connected to each other through a two-wire bus. The wires are a twisted pair with a 120 nominal characteristic impedance. CAN allows multiple devices, referred to as nodes. 2 or more nodes are required on a CAN network to communicate. The complexity of the node can range from simple input-output device or embedded computer or a gateway. Each node requires a central processing unit, microprocessor or host processor. CAN controller, often an integral part of microcontroller CAN transceiver. Okay, so this was some of the important and commonly used buses that were important for industrial communication. There are many other variants of even Modbus. Even you have variants of Ethernet and Profibus. So I think we have studied the basic ones, the really that were the or most commonly used ones. But if you want to look for more in detail, just go for in the book for industrial communication. There you will see that there are a lot of standards, and there are many more advanced forms also for communications. But this CAN bus, this is also quite commonly used and also advanced method. Profibus, Modbus, CAN bus, they are very popular actually. Yeah, so this is the end of the lecture, and if you have any questions, you can always contact me by email, or you can also contact me using the Zoom meeting. So thank you very much.